everyone. I'm happy to introduce our speaker today, Dr. Anton Vaks from the Geological Survey of Israel. Anton completed his PhD at the Hebrew University, working on Quaternary paleoclimate of the North Israel boundary of the Sahara Desert, reconstruction from Speleothems of Negev Desert, Israel. Anton did his postdoc at the Department of Earth Sciences at the University of Oxford, and also worked there as NERC principal investigator at the same Department of Earth Sciences at the University of Oxford. Research interests are paleoclimate, paleoenvironment, geochemistry and geochronology, and the link between human evolution and the paleoclimate. Please.
Hello. I'm very glad to be here again in Haifa University. Big pleasure. I would like to talk today about Speleothems as tool for reconstruction of paleoclimate in dry and cold regions, so deserts and permafrost regions mainly. And I will use two examples from Israel and Siberia. Before we start talking about paleoclimate, I would like to explain a little bit about the Speleothems, what they are, how they grow. So let's do it. Yeah. Okay. So Speleothems, stalactites, stalagmites, flowstones. Actually, when we talk Speleothems, we usually mean vaduz Speleothems, which grow in unsaturated zone, in caves which are above the ground level. So these caves are full with air and water flowing in from up downwards because of gravity. Now, there are also some kind of Speleothems that growing when caves are full with water. They called phreatic, but we will not talk about them today. And they mainly indicator for ground level and not for paleoclimate. So what I usually use for paleoclimate are stalagmites, flowstones, and stalactites sometimes. So here you can see stalactite with gross layers from Negev Desert, from a Shalim cave. Now, how these formations grow? Actually, when you have, you need to have carbonate lithology, limestone, dolomite. You need to have hard rock. If you have a rock which is soft, marl that contain a lot of clays, then any karstic cave that forms usually will be filled with clay very quickly, and no Speleothems will form. Usually you need clean limestone dolomite rock, hard, that can support the caves. You need to have precipitation, rain or snow melt above the cave that infiltrates through the soil and through the lithology below. So what happens with water, it catches CO2 in the soil, reacts with CO2, creating the carbonic acid that starts to dissolve the lithology below, and then when it reaches the cave, it deposits this dissolved limestone in form of stalagmites, stalactites, and flowstones. You must have flowing water, liquid water, to form these formations. Because else, if you don't have water, like in the desert, or if you have frozen conditions, you will not have Speleothem growth in the cave. Now, okay, so my method is actually to use Speleothem growth layers to find when water was flowing to the cave in arid regions, or when there were warm conditions in the cold region that is now permafrosted. And I used to date layers of stalagmites or stalactites, and then I know when these periods happened. Now, two questions. How this method can help us to understand climate dynamics on the long time scale? And another question, can it help us to predict the climate of future warmer world? We usually we do paleoclimate to understand the natural actually dynamics, which factors affecting climate, which natural factors affect climate. And then we can understand also what we do to climate with our greenhouse emissions. I'll try to answer these two questions here. Now, paleoclimate of arid regions, example from the Negev Desert is my first part of the talk. It will be two parts in this talk. First is about the deserts, about the paleoclimate reconstruction in the desert. The second part will be about the Siberia and in reconstruction of paleoclimate in cold permafrosted region. So, how actually deserts of the world form? Deserts of the world form in three circumstances. The first and most common is a subtropical high pressure zone. So we have air rising in the equator, in the ITCZ area. Then it's sinking here. So here it gets latent heat from condensation of water, and then when it's sinking here, it warms up because of this latent heat and dries up. So it forms this belt of subtropical highs, subtropical deserts. Now it's usually happens in closer to western coast than to eastern coast. So, for example, in Kalahari, you see here the desert closer to western coast and not to the eastern coast, because it's not only headley cell, but it's also ocean currents that control the desert formation. For example, if you have cold current on the western coast, you usually it stabilizes the air above it, and you have a high pressure. If you have warm current on the eastern coast, usually the air is not stabilized. It's warm and it's rising up. So even in subtropics on the eastern coast, you frequently don't have a desert. Whereas on the western coast, you do. So the sea currents, it's a second factor creating the desert. And the third factor, it's usually rain shadow and extreme continental position. If you have a mountain range that blocking the rain and the snow getting into the continent, then you usually don't get humid environment on the other side. And then there are a lot of deserts that form in this way. In Israel, this is the Dead Sea Valley Desert, the Judean Desert, and for example, in many places like Kazakhstan or Turkmenistan, it's also some kind of rain shadow. When you have very continental position, the westerlies cannot bring the air, the humid air there. Okay, so this is a map of the world deserts, and you can see all this. This is the belt of subtropical deserts. These are cold deserts that from areas that not get precipitation from westerlies because of mountain ranges and other factors. And you also can see these deserts on the western coast of subtropical areas because of cold currents, like Humboldt current here near Atacama and Benguela current near Namib. If we look on these weather systems affecting the boundaries of the deserts, so you can see, for example, that westerlies, they affect these cold deserts, and if they are stronger, they may bring precipitation to them, and they also affect the northern boundary of the subtropical desert. Now, the southern boundary of subtropical desert is affected by monsoon. So if monsoon is stronger, also the boundary, southern boundary will go to the north. And if we study paleoclimate of the deserts, for example, in the southern part or in the northern part, we can also get a picture of the dynamics of different climate systems. So when they became stronger, when they became weaker, and how these fluctuations actually relate to the global climate changes like glacial, interglacial periods, solar activity, and other stuff. So then we actually, if we know these dynamics, we also can understand what may happen in the future with these systems. If we warm up, what happens with them according to what we have seen in the past. Okay, so effects of future warming on the desert and their margins are actually two contradicting effects. First is if we have more evaporation of the water from the oceans during the warm climate, we actually bring more moisture into the continents from the oceans. But also there is another effect. If it's warmer, then soil losing moisture very quickly. So we may have more rain, but it will not stay in the soil, and actually many regions may get negative water balance, even if it's more, actually theoretically more moisture rich this area. So, and we need to know which of the two effects will win eventually. And then there is a modeling that trying to do it. For example, this is a Hurling paper of 2012. Then he actually tried to find a model explaining the aridity of Mediterranean that developing during the last 2-3 decades. And he tried, this group, they tried to explain this trend by different warming scenarios. So they found that if we have a global warming of 0.5 degree, we get aridity, but not like this, only maybe in the Middle East. And if we have warming above Indian Ocean by 1 degree and tropics by 0.5 degree, we get more aridity than we actually have. And only the scenario of warming of the tropics by 0.5 degree actually shows something similar to what we have here. So this is interesting work, and I think it's contributing very well to understanding the global warming, but I don't think it's giving a full picture, because we also need to look on the warm periods in the past and see how they affect in this region, and then to compare to the model and maybe add the results to the model. So we go to paleoclimate, and it can show us how the climate system works on the long-term scale. And my research objectives in the deserts were to assess when the deserts and semi-desert were extended in our area in Israel, and maybe in other regions if I can, and understand the relationship between global and climatic cycles and the extent of the arid regions. And if I use stalagmites to know when the water was in the desert, I need to date them radiometrically. And then I need to use uranium-thorium method if it's less than 500,000 years, or if it's longer than 500,000 years, we need a uranium-lead method. So actually usually uranium-lead method is based on two chains. Chain of 234, 238 uranium to 206 lead, and 235 uranium to 207 lead, but usually we have very little 235 uranium in this in Speleothems, and the amount of the lead 207 is very small. So usually we use only this chain for chronology. Now, so we have this father, let's say, that's producing all the intermediate isotopes. The two isotopes with the longest period of half-life is 234 uranium and 230 thorium. And this actually, when we date the young stuff, then we need only the ratio between formation of 230 thorium and its disintegration rate. And in the beginning, the rate of formation is very high, and then when we approach 500,000 years, then the rate of formation becomes almost equal, or actually equal to rate of disintegration, and the method stops working, and then we need start dating by uranium lead. Now, what happens in speleothems is that usually uranium is very mobile in solution in oxidizing conditions. It creates uranyl ion, and this uranyl ion enters the lattice of calcite or aragonite or carbonate, any carbonates that forming, and then we get these two. But if it's clean and we don't have no clays, we don't have thorium in these crystals, and then thorium starts forming by radioactive disintegration, and then it's growing until the equilibrium forms here, and the chain continues down. And okay, so this is a theory of dating, of chronology, and I will go to results. Now, before I go to results, I want to explain another term I will use here, which is marine isotopic stage. It's actually glacial and interglacial periods, all these oscillations. This is time scale of last 5 million years or a little bit more, and these are benthic stack oxygen isotopes and benthic foraminifera, and they show actually the ice volume. So when we have a lot of ice, then most of the O16 goes to the ice caps, and then we get the sea heavier. Then we get the sea, heavier. So in glacial periods we will get low. This scale is overturned because this is colder and this is warmer. So this is ice glacial periods are here, and interglacial periods are here. And there are several cycles of that causing this to form. So these are precession cycles that were dominant here in old times. Then 42,000 year cycle and 100,000 year cycle. I will not talk about what caused this evolution of climatic changes. I'm just saying that both three cycles are present now, but now the 100,000 is dominant. And this, so this is Pliocene. This is Pleistocene transition, and this is a Middle Pleistocene transition. Okay, so we will start talking about paleoclimate in our area. So this is a research area of my PhD that was in the Negev Desert, and you can see all these dots are caves. So from actually Malay Ephraim Cave, which is in the Dead Sea Valley, Jordan Valley here, through northern Negev to the central and southern Negev Desert. Now, this is Mediterranean climate, the green one, where Sorek Cave is located. And this area is transitional steppe zone or semi-arid zone between, let's say, 300 millimeters of rain and 150 millimeters of rain. And this is the desert area in the south. And we will see that periods of formation of speleothems are completely different in the three zones. Now, so first I will talk about transition area of semi-desert or steppe zone. This is record of mainly two caves, Tsavoa Cave near Arad and Malay Ephraim Cave in Jordan Valley. The records almost similar, the same periods. And this is photo from Tsavoa Cave from here. And here two speleothems. This is a perpendicular cross section of stalactite, and this is a stalagmite of last glacial period. And this is the previous glacial period. This is a small piece of interglacial between the two. And if we look on the results, then this is a picture that we get. These are marine isotopic periods. So this is interglacial, this is glacial period, this is interglacial again, this is glacial again, and this is a Holocene interglacial in which we now live. We actually live in Anthropocene, but it's a continuation of Holocene. These are speleothems. And this is a time scale, and these are their ages of these speleothems. So you can see actually that they cluster mainly in glacial periods. You can see here we have a lot of deposition during the glacial. Here we have another cluster of the deposition during the last glacial. And we have some interglacials as well. We have this one here, stage 7. We have the 5E here, but here in this period we have almost no deposition. We have dry period here in interglacial, and in Holocene we also have dry period. And it's if we look on compare with lakes, then we see that it's very similar to Lake Lisan. We have high level of Lake Lisan here, when we have Speleothems in semi-arid zone, and then we also have high level here in this period. We have some temporary high levels here in stage 5E interglacial, but most of the time in interglacial we have low level, and in Holocene we also have low level. So we have less water in the system during interglacials. And this is what we see in semi-arid zone. Now in the arid zone, what we have, when we go to all these caves in the extreme arid zone of Israel, then we see something different. We see that all the glacial periods disappear. So we don't have actually in glacial periods deposition there. The rain haven't reached this dry area of Israel during these periods. But we do have the interglacial periods here in stage 7, for example, and beginning of stage 5, they remain. They were in the semi-arid region, and when we move to the arid region, the glacials disappear, but these periods remain. And if we look on the spatial picture, you know, the time and space, then we see that what happens here, this is Sorek cave in humid area. So in Sorek cave and Pekin cave, deposition is continuous. Speleothems grow all the time. So this is time scale, this is glacial periods, and this is amount of precipitation from the north to the south, yes? So what we have here in green area, that we have continuous growth of speleothems. Then we move to the semi-arid region, and then we get deposition in glacials, and intermittent deposition in interglacials. We have only some periods in the interglacials when we have water, but there are also a lot of dry periods. So there is water not always, rain not always comes in glacials, in interglacials, sorry. But almost always we have enough water in glacials. And if we go to the south, then we see these two episodes continue into the desert, somewhere until maybe here in Malea Mishar, 50 millimeters as a height, we still have these two. Here, I haven't found these periods, except maybe on small one age here. So we have this less rain from the north to the south, but in these periods rain reach the central Negev at least. So our preliminary conclusion that glacials generally wet, but the storm intensity seems to be moderate because no moisture reaches the desert zone. It's only semi-desert wet. And the interglacials generally dry, but with occasional wet episodes with strong storm penetrating deep into the desert. Okay, so why it happens? Why we have increase in humidity in semi-desert during the cool periods? First, there was a work of Banasi that worked in Dinarian karst in Croatia, and there was a very interesting. It was very interesting work because it was a mountain like Mountain Hermon, and it's they know how much rain falls on this area. And then this water penetrates down, and everything gets in one river from the cave. So you can actually analyze how much water you get in and how many water you get out. Now, what he found that during the winter, when temperature was +3, you actually get almost all your water that's falling on the mountain. It gets out with the river. So 95 or 98% of infiltration of water. So all the water, almost all the water in the winter remains in the system. Now, when temperatures start to rise and get to 10 degrees, 12 degrees, you remain with half of the amount. And in the summer, when you have maybe 20 degrees, 25 degrees, you remain with 15-20% of the amount. So you get the amounts of precipitation in this area, they are equal in summer and in the winter. And if you, also when you have a lot of rain in the winter compared to summer, then you have more water remaining in the system than when you have a lot of rain in the summer compared to the winter. So then we know that the temperature affects very much how much water you finally get in the system when after your if you get the same precipitation. Also there were work showing that cold winters are rainier than the warm ones in our region. And also there is work in the Sorek cave that's showing that most of the meteoric water infiltrating into the cave fall in temperatures below +10, and above +10 all the rain events are they're usually negligible to water budget. Now, we actually, you remember this map of the work of modeling in the beginning. So, and it shows a big aridity as a result of tropical warming by half degree. And actually in Mediterranean we have a lot of aridity during the last 20-30 years. And there are works showing that this aridity actually contributed to Syrian civil war. Because of course there were a lot of problems, other problems of water management in Syria and government problems, but when you get such drought, you actually cause agriculture in semi-arid regions of the country to collapse. And then what I tried to, when I put the area of semi-arid, for example, this is Israel compared to Syria, precipitation maps. And if I put the semi-arid region of Israel and Syria on the map, by yellow, you see, in Israel it's narrow belt, but in Syria it's huge area. It's something that maybe almost half of the country, between 150 millimeters and 300 millimeters. So if, and we see from the Speleothem study that this area actually vulnerable to droughts because of the high temperatures. So cool temperatures, we have positive water balance here. But when the temperatures are warm, they actually, this area becomes desert. And if we see what's the area in Syria, all this area is Syrian Jazeera, where a lot of agriculture is located. So before the drought, they had maybe 300 millimeters, and they could do some agriculture. And then they suddenly started getting 200 instead of 300. And then what happened that these farmers get bankrupt, and they flooded the cities looking for jobs, and the property prices rose up, and then we actually have troubles. So this is a way how the Speleothem study of the semi-arid region also can say us which areas are actually vulnerable to climate warming and climate change. So here we can see this example. And okay, so now this actually made our conclusions of the desert study that in semi-arid regions of Levant, cold conditions usually favor a more moist climate than the warm ones. And hot climate reduces the water security in the region. Yeah.
But you didn't answer why in desert areas you actually had the more water during interglacial periods.
I had also in these two episodes that I showed there, they happened also in semi-arid regions as well. But it's not something that you can trust. You do have these extreme events, but it's not something that if you talk about general conditions, you usually drier, but sometimes you get extreme events and you have periods with extreme flood events like these two periods in the stage 5.5 and stage 7.1. So these, there is We still don't know where they came from, but this there is a possibility it came from Mediterranean system, or it could come from a tropical system as well, because we see some correlation with monsoon index. But these events can happen, but in general you see the aridity in warm periods.
Because on the other hand, there are also some geomorphological phenomena like Nakhatzin, the canyon in Nakhatzin, that
Yes.
show you that at some period in the past,
Definitely, yes.
there had been a lot more water in there.
It's definitely yes, but what happens actually that when you, as I said in the beginning, when you warm the climate, then you take more humidity from the oceans, you bring it to the continent, so you're supposed to get more water. But you also have the negative event, negative effect of evaporation that is more intensive on the continents. So you definitely can get extreme event of high rain. Can you trust it? I'm not sure. Okay. Now, yes.
Just a comment on this. Maybe with warmer waters, the Red Sea trough can be stronger at those times.
Could be, or tropical plume. Also tropical plume could be. We haven't found the evidence during our research, but there are other studies that showing that it could happen. It could also be a Mediterranean region, but we still don't have proof to one side or to another. Decrease in the water from the north to the south still points to the Mediterranean, but there are more studies that saying that maybe tropical plume is responsible, and it's bring to precipitation only when it interacts with jet stream above Mediterranean. So even if it's tropical moisture, if it's not precipitated above Sahara, it may precipitate only above our region. But it's still speculations. It's no proof to anything. Okay, I want to talk about permafrost now, and. So in my postdoc, I did work in Siberia, trying to use the same principle of Speleothem precipitation, Speleothem deposition, or absence of Speleothem deposition, as permafrost, as a tool to reconstruct the permafrost. Okay, so permafrost, it's area where we have freezing conditions entire year. And we can see that it covers about 25% of land on Earth. Siberian permafrost is especially extensive, but also Canadian ones and Greenlandic. We have continuous and discontinuous permafrost. So this area, for example, is discontinuous permafrost, and this one is continuous permafrost. Discontinuous is usually when mean temperature, mean annual temperature is between 0 to -5. In these conditions, we can still get, let's say, permafrost on northern slope of the mountain, but not on the southern slope of the mountain. But when we have temperatures below -5, we usually get continuous permafrost, except maybe below big lakes. And this is how it looks like in tundra. You see this ice below the grass. In taiga, in forest, sometimes you see trees growing here, and you see 1 or 2 meters of soil, and then in the depths of 2 meters, you start to see ice. So, what happens when the climate warms? It's, I think it's trivial to understand that when we warm climate, then permafrost goes to the north, the southern boundary goes to the north. And when we cool climate, then permafrost region expands, and I think during the last glaciers, permafrost covered most of the Europe as well. And there are works in Slovakia that showing that permafrost was present. And now permafrost covers only Siberia and Canada. Now, what happens when this permafrost thaws? When we actually have infrastructure. If we have infrastructure that's using permafrost as hard ground, then when it thaws, the infrastructure collapses, like the railways, like the pipes, like in electricity, and then we actually want to know how much we need to warm the planet so this boundaries will start moving to the north and, for example, affect the Yamal Peninsula, where a lot of gas wells are located. Yes, and there is a nice pipe going to Europe from here, like this. Now, what happens if it collapses? Then this pipe, Europe will not get a quarter of its gas during the winter, and so it will be cold. And then we will need to know what may happen here if we warm planet by 1 degree, by 2 degrees, by 3 degrees, by more. And then we study caves to do it. So when we get permafrost, this is frozen rock, this is active layer. Here we have roots of trees, of bushes, but water cannot penetrate to the cave. Cave is frozen, and there is ice in the cave. Now when we come to this cave, see stalagmites, and then we bring them to the lab and cut them, we see periods of growth. We see this one period of growth, and then hiatus, growth break, very long growth break actually, and then another period of growth. And we can know when it was warm, like here, then it was cold, like here, and then it's warm before. So, how we reconstruct the movement of boundary of permafrost to the north, to the south? We make some cross-section from the north to the south, like this. So we had, actually when project started, I wanted to try to catch two birds, to reconstruct permafrost here in Siberia and maybe desert conditions here in Gobi. So we took also the 2 caves here, with, but the amount of Speleothems was very small. So we finally focused on the north and on the permafrost. And there were about maybe 6 expeditions to this area from 2008 to 2014. And objectives were to find assessing when Siberia was unfrozen, when the Gobi was humid, it was a secondary target, it is a primary target, and understanding the relationship between global climatic cycles and the extent of the permafrost, and maybe of the Gobi Desert. Okay, so this is one cave located on latitude 60, and this is in a cave under continuous permafrost, but close to its southern boundary. And you can see the ice in the cave. In the cave it's temperature slightly below 0, but outside it could be much colder in the winter and much warmer in the summer. So when it's cold like this, you look like this. Now, if you go, but the cave is dry, you see stalagmites, but you don't see dripping water in the cave, it's frozen. Now you go to the south, to the Lake Baikal area, and there you do have active caves that drip now, but temperature is about 1 degree plus or 2 degrees plus. And so you have seasonal freezing in above some places where water is dripping, and patches of permafrost on the northern slopes of the hills, but it's dripping this area. And in the Gobi you see dry Speleothems again, but Speleothems are very rare, and they're here we thought it's with stalagmites. It wasn't stalagmites, it was some phreatic formation, so it was a mess. But finally, when we started dating them, it was very interesting. In the north we got old ages, and this was a younger age. In the middle area, near Lake Baikal, we got every interglacial period, but no glacials at all. And in the south we got 1 or 2 ages that we could date by uranium thorium. But this is a picture of ages, final picture of ages about this, the first part of the research, study of 2008-2012. So this is a time scale. This is a latitude between 60 and let's say 45. So this is central Siberia, this is southern Siberia, this is Gobi Desert. And these are names of the caves, amount of samples that were dated from each cave, but some of them were very old, so they were beyond the 500,000 range. So for example, in this cave we dated 15, but only one was here. This was the youngest one, and nothing formed here. Here in these 2 caves we got deposition in every interglacial. So here it's a glacial interglacial changes, and you can see that in interglacial we got Speleothems, but not in glacials. And this is temperature of Pacific whirlpool that is considered to reflect changes in global temperature. And we see that when global temperature was very high here, we got something in the north. But here, we didn't get nothing. And this was very nice story. By the way, in the Gobi also we saw something here. Maybe monsoon was a little bit stronger, but it was interesting to see, but it was too little amount of Speleothems to conclude something. But this picture was very interesting, and then we made a nice paper about it, and we were very happy. But when we went back in time with uranium lead ages, we saw that the picture a little bit more complex. So this was a story between permafrost and boundary zone on latitude 60. So when global temperatures rise 1.5 degrees above pre-industrial, this was major conclusion of what we did, and it was a lot of noise in media. But then we went to the past and saw something interesting. So when we extended the amount of Speleothems, we found again nothing was younger than 400,000 years, and it's good. It didn't contradict our first conclusion, but we saw a lot of ages in the far past. And then when we plotted them against the Pacific whirlpool temperatures, then we were surprised, because this here it's one of the warmest periods, and here was actually the last deposition period. So this is okay. This is a time scale. Yes, 1.5 million years, and this is also the time scale. Now this is glacial and interglacial cycles. This is Pacific whirlpool temperature changes in SST, surface temperature, reflecting the mean Earth temperature. Now here, these are our ages from the cave, and this is actually a function of how many ages we have. But what is important in this is this curve. So this is Speleothem thickness. So here we have very thick Speleothems, very big increase in Speleothem thickness. They grew very rapidly here, then they started to slow down here. There was another 2 jumps, and then they slowed down again. You see the gaps becoming bigger. Last period is here, and then frozen. But why? Here it's supposed to be the warmest period during this period on the Earth. So why here we have more deposition than here? So it's maybe not the Earth's mean temperature, it's something else affecting them. And then we started looking on the Northern Atlantic Ocean. And here maybe we have a key to solve this. It's still unpublished data. We try to understand what is happening. And we saw that in North Atlantic site 6 or 7, we have actually the SST goes down from Pliocene to Pleistocene. But here, for example, in middle Pleistocene, we have high temperatures, and here it's middle Pleistocene transition. We have this cooling of Northern Atlantic. It's become cooler, and also we have here, and maybe it's reflects the temperature of the Atlantic. Now, Northern Atlantic brings warm air to Siberia. There is a vessel is taking heat from Northern Atlantic to Siberia, and this way it may affect the climate of Siberia. Now, so if we put this graph here, then we see that here we have quite warm periods, warm temperatures of Northern Atlantic, and then we have this cooling, and then it's become colder. So this is middle Pleistocene transition, North Atlantic is cooling. So maybe this is a key to explain what is happening in Siberia. And now we're working on paper about it. I hope to find more data from the oceans about middle Pleistocene transition. It's very interesting period here.
Anton, the reason why you think it is you are not because there's less moisture because the North Atlantic is getting.
No, North Atlantic. It's when it's warm, you get these worms with with westerly winds to Siberia.
So because the temperature is getting
Colder.
so you have less water to transport.
No, less heat to transport to Siberia. Less heat.
With
not
the water.
with the water, yes.
Okay.
So if we transport less heat to Eurasian landmass, it's cooling down.
Okay.
And then we have this mid-Pleistocene transition. So these are our conclusions from this work. So we have here we have warm Northern Atlantic, and we have no continuous permafrost on latitude 60 in eastern Siberia. Then we have this middle Pleistocene transition with cooling of Northern Atlantic and cooling of Siberia. And after 400,000 years, we have cold Northern Atlantic Ocean and probably an establishment of continuous permafrost. And now I want, in the end of the talk, I want to talk a little bit about our preliminary results from here, from the far north of Siberia. So here, previous part of the talk was mainly about this cave on the southern boundary of continuous permafrost. And then we tried to find something here, but it was very difficult. It's an unpopulated area. And then we heard about Speleothems here in this area. And we went there in 2014. And it's very beautiful area. It's near Lena Delta. You see all these branches of Lena Delta. Here we have this mountain range that ending here. And there we found some caves in this area. And Speleothems that exposed also on hill slopes where caves were eroded, and also some caves, but in the cave it was very difficult to get in the caves. They are clogged by ice. But on the in places where caves were eroded, we found Speleothems on the slope. And when we cut them and dated them, we found that ages are 10 million years in uranium lead age. And it's Tortonian epoch, when in Israel it was the Bira formation, I think, Bira lakes. And when I started looking at literature about this period, it showed that global mean annual temperature may have been as much as 4.5 degrees higher than present day. So if we look on the map, it means I still need to figure out how far the landmass moved during the 10 million years, because 10 million years it's a lot of time, and maybe the continents shifted a little bit to the north. But Asia probably was more stable than other continents during this period. And if the movement was very small, it means that when we warm the planet by 4 or 5 degrees, then there is no permafrost at all in Siberia. So this gives us some range about what climate change how it can affect the Siberian permafrost. So if we warm the climate by 5 degrees, we may lose all this permafrost if we give it enough time. Okay, and there are a lot of good Russian guides that helped us in this work, because without them we couldn't get to any place far in the north. And there are also good guys that helped in the lab with uranium lead dating, and they actually enabled us to do all this amazing research. And thank you very much for your attention.
Thank you very much, Anton. Any questions, please? Okay, I see that there is no questions. Thank you again for your talk.